Yes, teacher. So I'm Yusuke Nakauchi, Rizumika University. So today I'd like to talk about the visible and near infrared microscopic hyperimage we are developing for Lunar surface mission. Next, please. So with the increasing opportunities for Lunar activities, developing a compact in situ analyzer for surface investigation is essential. So leveraging manned lunar activities to select and return scientifically significant lunar samples is expected to greatly advance lunar science. So previous studies suggest the upper samples and the lunar meteorites may exhibit breccias and breccia textures and thermal metamorphism, since they have remained lunar surface for extended periods. So in such case, brecciation and the thermal metamorphism make it difficult to obtain the initial information. Therefore, sample return mission, it is crucial to observe whether samples have remained unaffected by the brecciation or thermal metamorphism. Next, please. So we started to develop a compact Vis-NIR microscopic hyperimager for lunar exploration mission to investigate and select of the lunar samples. By observing the exposed area of the lunar borders with micron scale, scientifically significant lunar samples can be selected and returned. This camera is required to be mounted on the edge of the robotics arm and to make contact with the surface of lunar borders. Additionally, we are developing a grinding tool for processing rock surface on the moon. Next, please. Okay, this is detail of the microscopic hyperimager. This camera has the diffusion light source using the grating and the SWIR detector. The observation wavelength range is from 750 to 1700. The right figure shows the reflectance spectra of lunar surface materials. The red area is the observable wavelength range. This camera is required only temperature stability from the 0 to 40 Celsius degree during observation. The spatial resolution is 10 micrometer per pixels. Next, please. So this next figure is a BBM of the breadboard model of the microscopic hyperimager. Okay, the light source unit connected to the camera unit through optical fiber. The spectroscopic light is delivered to the illumination position via the fiber. The BBM allows the selection of the two illumination methods for experiment. Yeah, we chose the illumination position. Okay, next, please. Okay, so we do experiment using the breadboard model. To evaluate the spectroscopic performance and the impact of the high spatial resolution on sample analysis. So, we measured the lunar meteorite. Two cameras, microscopic hyperimager and the multiband camera, were used for the measurements. The multiband camera MBC was the onboard stream. The microscopic hyperimager has a spatial resolution of 10 micrometer per pixels, while MBC offers a 110 micrometer per pixels. Additionally, microscopic hyperimager provides a continuous spectra, whereas MBC is multiband. Next, please. Yeah, this figure is the result of the result image observed MBC. The texture is very distinguishable, but not sufficient. Next, we overlay the imaging captured with a microscopic hyperimager to better visualize results. Okay, next, please. Okay, this is the result image observed by microscopic hyperimager. So the texture is clearly distinguishable. At the resolution, rock texture such as the cracks provided previously invisible at the MBC data can now clearly observed. Since this image was obtained by hyperimager, each pixel in the image contains reflectance information. So next, please. Now let's take a look at the reflectance spectra of these three spots. Okay, next, please. Okay, they are the reflectance spectra obtained from the MBC and the microscopic hyperimager. The vertical axis is the normalized reflectance, and the horizontal axis is the wavelength. The diamond-shaped plots represent the MBC data, while the small circular plots shows the data acquired by the hyperimager. The spectral shape of the both datasets are similar, and the absorption feature are clearly captured. Okay, next, please. The next figure is the RGB image using MBC's data. The boundaries are easier to distinguish compared to the monochrome image. However, the feature such as the cracks caused by metamorphism can't be identified. Okay, next, please. So next is the RGB image using the microscopic hyperimager. The boundaries are clearly identified, captured compared to the monochrome image and the MBC's data. The cracks caused by the metamorphism is identified. Furthermore, in the center green area, textures are indicative of the partial melting were observed. By acquiring high spatial resolution data on the lunar surface, it becomes possible to determine whether the observed samples have undergone metamorphism. Okay, next, please. Okay, this is summary. So we are developing the compact visible NIR microscopic hyperimager for the lunar exploration mission. It could obtain high spatial resolution image and continuous reflectance spectra. By using this camera, advanced sample analysis can be conducted on the lunar surface, significantly contributing to the selection of the return samples. Additionally, we are developing a grinding tool for the processing rock surface on the moon. Okay, so using near-infrared spectral features, it is possible to add color to the gray lunar landscape, with which may serve as a useful navigation aid for the pressurized rover. We will continue to investigate whether this near-infrared spectral features can be used as a navigation indicator for the robotics arm. Thank you.